Hello everyone and welcome to the lesson for 10.2, Simplifying Radicals. We're going to jump into chapter 10. You may have heard of what radicals are or square roots, but we're going to delve a little bit deeper into how to simplify square roots. If you look here in the directions, it says this lesson will help you simplify radicals into what's called exact answers. I am going to underline that much better, right? This means you are not rounding and providing approximate values. So in some sense, we're going to use the calculator for this lesson, but we're not going to use it to do some rounding, all right? So what this lesson is going to provide is how to simplify radicals into exact answers. Now, this example here, we know the square root of 25 is going to equal 5, right? Because that comes from 5 squared, which is 25. But what happens when we have these? What happens when we have these kinds of numbers? Right? These are not perfect square numbers because if you go to your calculator and do square root of 20, this is approximately maybe 4.5-ish, right? But that's exactly what the point is today. We don't want an ish, we want exact answers. Before we get into it, we're going to first label parts of a square root symbol here, all right? So you can see the labeled parts here, all right? The number inside is what's called a radicand. We know the square root symbol, that's also called a radical. And then in this little v portion of the square root is what's called the index, all right? Now, if there is no number written for the index, it is assumed to be a 2 or a square root. Because sometimes you're going to have, and not in this class, but you could have what's called a cube root, you could have what's called a fourth root, etc., etc. All right, so when there's nothing there, right, which I think most of us, this is probably what we're used to seeing, it's actually understood that it's a square root. There's a 2 there, but we just never write it, okay? So how do we know if radicals or square roots are simplified? There are 3 conditions here. I think some of these will make sense a little bit more in the following lessons, all right? But pause here and take a look at it real quick. But we're going to get into an example. I'm going to show you 2 ways to simplify radicals here, all right? One is called identifying the perfect squares, and the other one is called using factor trees, all right? Now, you could easily go to your calculator and do the square root of 24, and when you do that, this is roughly about 4.9, okay? But again, we don't want that today, all right? So I'm going to erase that, okay? And when we talk about identifying perfect squares, here's what we mean. So what I like to do when I first teach this is think of numbers that multiply to 24, all right? So I'm going to list these out right here. So what I'm looking for is within a pair of these factors, right? These are the factors that, or the pairs that multiply to 24, right? But when I look at these, I want a pair where at least one of them is a perfect square number, right? For instance, let's look at this 2 and 12, right? If I were to take the square root of each of those, right? Neither one of those is a perfect square number, okay? The square root of 2 is like 1 point something, and the square root of 12 ends up being 3 point something. Well, that doesn't really help us, right? So I'm actually not going to use this one. I'm not going to use 1 and 24, right? Even though 1 is a perfect square, but that doesn't really help us. And 3 and 8, well, square root of 3 is not a perfect square, and the square root of 8 is not a perfect square, so I'm not going to use that. Now, okay, so by process of elimination, we have to use this, right? But you're going to see why this works. So the square root of 24, and this actually kind of leads into tomorrow's lesson that Mr. Szabo is going to teach us. the square root of 24 can be written like this, right? Square root of 4 times the square root of 6, because 4 times 6 is 24. Now we want to use this one because we also know that the square root of 4 comes out nicely to be 2, right? But then the square root of 6, it's not a perfect square, so what do? We leave it. And this is your exact answer right here. 2 square root of 6. All right. Now if you go to your calculator and if you do 2 times square root of 6, guess what? It's going to give you whatever square root of 24 is, because these are equivalent. All right. So we are not going to round. We're going to use the exact answer of 2 root 6. All right. So let me show you another method here using factor trees, because some people might prefer this way, right? And so how do factor trees work? Think back to in elementary school when you come up with factor trees, right? So for instance, I don't know, we could start with 8 and 3, right? And 8 we can split up to maybe 2 and 4. Okay, now 3, I'm going to stop here because 3 is a prime number, so that's when we just stop. 2 is a prime number, so I'm going to stop here. The 4 I can keep going, and we know that's 2 times 2, right? So what I like to do is I like to underline all of my factors that I end with, right? Because these numbers, 2 times 2 times 2 times 3, is what multiplies to 24. So what I'm going to do is this. The square root of 24, I'm going to rewrite it like this. So I have the factors written out in under the square root, right, as 2 times 2 times 2 times 3. Well, now what? Well, so as I've taught this in the past, one silly way that I've come up with, as a strategy is if you think of the square root as, I don't know, some sort of like barrier, okay, then what do? For every pair, right, they pair up together to become one, right, to bust out of or go through that wall, right? So these, since there's a pair of 2's here, they kind of quote unquote become one, right? They become 1, 2, right? So that 2 comes out, okay? But this 2 is by itself, and this 3 is by itself, so there's no other 2, there's no other 3 to pair up with, so unfortunately they're kind of stuck inside, all right? And so these guys just multiply to each other. 2 times 3, right? We know that's 6. So inside the square root, we have the unfortunate 6, and the 2 got to come out, all right? And see, we end up with 2 root 6 still, okay? So you could break it down into factors if you'd like, or you can find pairs that multiply to that number in order to identify perfect squares, right? If you want to try this next example on your own, you can pause it, right? Or you can just keep watching here. So here I've listed the factors, the pairs of factors that multiply to 80, right? And we're looking for a pair where one of them has a perfect square number. I'm noticing this one right here, okay? 4 and 20, because I know that the square root of 4 is going to be 20. Now here's the thing, when you do these types of problems, all right, it might be helpful to look for the largest perfect square. So if you look one more row down, look, there's 5 and 16. And 16 is a perfect square because the square root of 16 is going to be 4. So I'm going to use this one. Now there's nothing wrong with using 4 and 20, but that means that you might have to simplify the 20 as well. But I want to try it and do it in one shot. So I'm going to write the square root of 80 as the square root of 5 times the square root of 16. All right, because again, we know that the square root of 16, this equals 4, right? Okay, and square root of 5 is just square root of 5, so that's square root of 5. Now, to avoid confusion, right, someone might accidentally make it look like square root of 54. I'm going to write the 4 in front. So this is 4 root 5. Okay, again, because we used the higher perfect square. Now if I use the factor trees, I'm going to break down 80 to make my factors look like this. Right, here's my factor tree, and I'm also going to underline my prime numbers, right, the factors that I end with. And I've rewritten those factors inside the square root, right? 2 times 2 times 2 times 2 times 5 multiplies to 80, right? And so we said every pair, right, they pair up together to bust through this wall, right? They become 1. So 1, 2 comes out. There's another pair of 2s. They pair up together to become 1, and they bust out, all right? But then unfortunately, 5's by himself, so the 5's kind of stuck, all right? And so what you end up with is the 5 is by itself inside. Now, 2 of these 2's came out, all right? So that's actually 2 times 2, and that's 4 root 5, which is what we had the first time around, all right? So the same applies even when you have a coefficient out in front, right? Like there's this 2 already out in front. I'm going to focus on the square root of 12. These are the pairs of factors that multiply to 12. And I'm going to use 3 and 4 because I know that the square root of 4 is going to equal 2. So it's going to look like this. So again, square root of 4, this equals 2. And this 2 and the original 2, they're going to multiply, right? So that's going to be 4 root 3. Okay? You can pause here and try 5 square root of 27. And there's my work real quick. You can pause here, take a look at it, or you can move on. You can also pause here if you'd like and try these problems. Or also move on to the last couple of examples that we're going to look at for the Pythagorean theorem. And here are answers and work to pause here and check if you'd like. Now there's a famous theorem called the Pythagorean theorem by the Greek mathematician Pythagoras, and he discovered that there's this relationship for right triangles only. If you have a squared plus b squared equals c squared, or to be more accurate, if these are the legs, right? These are called the legs, and the side that's the longest, that's across from the 90-degree angle, the longest side right here, is what's called the hypotenuse, right? The hypotenuse. And so to be a little bit more accurate, this is what the Pythagorean theorem actually says. The leg squared plus another leg squared equals the hypotenuse squared. All right, so we're going to use this relationship for the next couple examples. So here in example 1, I've labeled the hypotenuse as C because again, I know it's across from the 90 degrees, so it's the longest side. So these are the 2 legs here. So my setup is going to look like this. Right? 3 squared plus 4 squared equals C squared. And I work this out. Right? The next step, I'm going to get 9 plus 16 is equal to C squared. 9 plus 16 we know is 25, and then we have c squared. And then how do we solve for c? We do the square root because we have to do the inverse, and the square root of 25 is 5. For this final example, I know that the 7 is the longest side because it's across from there's supposed to be 90 degrees here. Okay, so you got to be careful of what your setup's going to look like here. And so when you solve this out, after a couple steps, here's what it looks like. And then you have to simplify this radical of square root of 24. And as you can see, I showed both ways.